All right, what did we talk about yesterday?
Double derivatives. I mean, double integrals.
So let's talk about double integrals, and let's just do a bunch of examples until we get really good at it. So here's our first example. We want to integrate this xy as the integrand over the domain D, where the domain is enclosed by a couple of curves. Y is equal to x squared, and y is equal to 3x. So let's take a look at that two-dimensional drawing first. So y is equal to x squared looks like this, and we have a line going through the origin with slope 3. And so I'd be interested in trying to figure out where that thing is going to intersect. Clearly it's going to intersect at 0, 0, but then we need to figure out where the y is going to intersect here at the second time. So if we set the y's equal to each other, you get x squared minus 3x, or let's just say is equal to, and then x squared minus 3x is equal to 0. So x minus 3 is equal to 0. So I get the x value here to be 3, and then the y value to be 9. Okay? So by doing that legwork in the beginning, you get kind of an idea of how you might be able to approach this. All right. At this point, we can still have a choice as to which variable we want to integrate with respect to first. So we can set this up in two different ways. I think it's a good exercise to set this up in two different ways just to get used to setting up double integrals. And then also, if you set it up one way, you decide you might need to go a different way just for the sake of being able to integrate the integrand, then you should know how to set it up either way. So let's first set this integral, evaluate this integral with respect to y first. So I'm going to set up my inequalities that would then follow my double integral here, my iterated integral. So remember, if you want to integrate with respect to y first, you're going to draw a line parallel to the y-axis going into the region and out of the region. So where you enter the region, by the way, parallel to the y-axis going from negative to positive, right? Going in the positive direction. So I'm going to enter my region at y is equal to x squared, and I'll be inside of my region until I exit my region at y is equal to 3x. What are my limits for x?
Constants.
They're constants. Damn straight they're constants. And they're going to go from 0 to 3 just by looking at my x limits. Okay? So that's one integral set up. I will integrate xy first with respect to y, going from x squared is my lower limit, my upper limit is 3x, and then my x, the outer limits here are constants going from 0 to 3. That looks innocent enough. We should be able to do this integral. But for some reason, if we couldn't, we might need to switch the order of integration. And when you switch the order of integration, my goodness, don't just switch the integrals with the same limits, right? Because what would happen if you switched like that? You wouldn't have constants on the outside. And you know that you always, always, always have to have constants on the outside. So let us redo this integral by integrating with respect to x first and then y. So if I integrate with respect to x first, I would draw a line parallel to the x-axis, and I would see when I would get into my region. And I see when I would get out of my region. All right, so I get into my region through this relationship between x and y is equal to x, y is equal to 3x, but I need an x. X is my dependent variable there. So I need to solve for x here. X is equal to what? Y over 3. So that would be my lower limit. I would be inside of the region until I get out of this with this relationship where I need to solve for x. So x is equal to what here? Square root of y. So those are going to be my limits for y if I decide to integrate with respect to y first. X if I integrate with respect to x first. Okay, what are my y limits? Constants. 0 to 9. So if I integrate this with respect to x first, my integral will look like the integral of x times y dx, x going from y over 3 to square root of y, and then dy going from 0 to 9. Okay? I can almost feel that nobody's going to make that mistake and make sure that constant, what?
You don't want to make a statement like that.
That's why I said almost. I can almost feel like, I know I'm going to see that mistake. I know. And when I do, should I take a picture of it and post it up? Man, had I done that over the years of teaching? It's one of those that, like, if I get a nickel every time somebody makes that mistake, might have 45 cents by now. Okay. That's a good warm-up example. Yeah?
So that's as far as we're going to have to go to set up the integral?
Well, let's not. This integral isn't bad. I would expect you to be able to do this by hand. I would expect you to know the basic integrals, like even the 1 over 1 plus x squared business, that's the arctan. I'd expect you to know that. But I probably wouldn't, in a timed test situation, I probably wouldn't ask you to do any integration by parts or partial fractions or anything like that. Now, if I decide to give you a take-home portion for that, I would expect you to be able to do those even if you just punch them into Wolfram alpha just to get a number. So that'll be the deal. Okay, more examples. No, let's do number 15, 16. Let's do both. So let's do 15. We have double integral y dA. So y, the inside function, the integrand is just y. But again, we're more concerned about the region D. So you need to be able to draw this and figure out what this thing might look like. So the region looks like it's x is equal to y squared, so that's a sideways parabola. Remember our conic sections? Yeah, it's all going to come back. X minus 2, so this has a positive slope starting at -2, so it'll go like this. So it'll probably be hitting at a couple of points over here. So again, we're going to be interested in finding out those points, so we should probably find a way to set them equal to each other. And normally we would set y's equal to each other, but this x over here has a y squared, so I would probably want to solve for x and set the x's equal to each other. So let's see, x is equal to y plus 2, right? And then I would set y plus 2 equals y squared. Set the x's equal to each other. And then get y squared minus y minus 2 equals 0. So factoring this, we get y is equal to something. So plus 1 minus 2? Minus 2 plus 1. So our y values are -1 and +2. So the x is probably important also. So either of these functions would work. If we put the y value in there, we should get the same x value. So like if we put y is equal to 1 here, we get x is equal to 1. And if you put y is equal to -2 here, x is going to be equal to 4. What?
Y is equal to +2, so x.
Oh. Y is equal to 2, x is equal to 4. Okay. So is that good? So now that we have that business, we will set up our integral. Now, if we integrate with respect to y first, we're going to have a bit of a problem. Let's take a look at the problem. If we integrate with respect to y first, we see that we go in through one function and end up in another. But if we take a look and go all the way over here, integrate with respect to y first, we have an issue with the way our function is set up. All right? So my attempt of integrating with respect to y first, it's probably not going to go very well. You see how you make these vertical cuts, and at some point over here, it's going to cut differently from one side to the other. We could do it. You have to break it up to two double integrals, which we probably don't want to do that. So this is more difficult. So let's cross this out and move on. And let's integrate this with respect to x first. So if we integrate with respect to x first, we would be drawing a line parallel to the x-axis. And now, regardless of what line you draw, you're always going to enter through one function and exit through the second function. And both of those functions will remain the same throughout your possible x or possible y values. So if I take one of these, I enter through the function. What is the function that I enter through? So x is equal to y squared, and that's going to be my lower limit. And then I'll be inside of the function, and then I'll exit the function here. And what is that function that I exit out of? X is equal to y plus 2. What are the limits for y? Constants. negative 1 to 2. Okay, you're all set. Or the integral is all set. So our integrand is just a function y, where we decided we were going to integrate with respect to x first, and our x limits are y squared to y plus 2, and then your y limits are constants going from negative 1 to 2. Okay? This is starting to be fun, isn't it? All right, let's try another one. So here we have y squared e to the xy as our integrand, and our domain is bounded by, we have y is equal to x, that's that diagonal, x is equal to 4, y is equal to 4, that would be up here. Let's label this, y is equal to 4, y is equal to x, and x is equal to 0, that's the y-axis. So I can see where my region is, right? So figuring out your region is back in Calc 2 where you're trying to integrate something to revolve around something, and you try to figure out what region you're revolving. It's the same exercise, trying to figure out from a bunch of functions that they give you, try to figure out what you're integrating over. Now, it looks like I can integrate with respect to x or y. Let's set it up both ways and see how either of them would look. Let's set it up with y first. And if I were to find the integral with respect to y, I would draw a line parallel to the y-axis and figure out what functions I will hit as I enter and exit the region. And I see that I enter the region when y is equal to x, and I exit the region when y is equal to 4. I didn't figure out what my points of intersections were, but maybe you can figure out what's my x limit to what? 0 to 4. So that's x equals 4 here. So that's how far I go. Okay. So let's see how this is going to look like when we put it into our integral. We have y squared e to the xy, and we decided we're going to integrate with respect to y first, and that y goes from x to 4, and then with respect to x, and that goes from 0 to 4. So do I want to integrate with respect to y first? No.
No, that's a double high
So it looks like there's a y as an exponent and a y in a polynomial, so you're going to have to use integration by parts a couple times. So maybe we'll try it the other way and see if that's going to be any easier. So we're going to set up our integral. This time we're going to integrate with respect to x first and then y. And we go back to our graph. We're going to draw a line parallel to the x-axis and figure out when we're going to enter and exit our region. We enter our region when x is equal to what? And we exit our region when x is equal to y. And then our y limits go from 0 to 4, constants. So our integral will look like y squared e to the xy with respect to x, dx, that's dx, going from 0 to y, and then dy going from 0 to 4. I don't know if it looks much easier, but your first step at least is not a, it's not integration by parts. Let's do this just for fun. So let's do the inside integral over here. We integrate this with respect to x, so y squared is a constant, y is a constant. So if we integrate that, what are we going to get? E to the xy divided by y. After u substitution, right? And then we're going to put 0 and y in. Well, let's just go ahead and cancel that. And then what we have is one of the y's is there. The x is going to be a y. So let's call that y e to the y squared. Is that right? Minus 0, because y is equal to 0. We only canceled one of the y's up on top. All right, so now our outer integral from 0 to 4.
X is equal to 0. I feel like e to the y. Yeah. It's e to the 0, which is 1.
So there's a minus 1. Okay. So our integral, the inside integral is going to be this, and then so now the outer integral is going to be y e to the y squared minus y dy. So now it's not an integration by parts, it's just a simple u substitution, and then you just have a minus. So can I just put dot 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 here? I'm just going to put a dot 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 because that's just too easy. No, I'm not kidding. I mean, I'm kidding. Not too easy, but it's easier than having to do the integration by parts twice, is my point. You know, books, they say sometimes they will leave it up to the reader to finish the proof or to verify that this is true. You do it. Of course, one time that happened in history, Fermat was doing some complicated stuff, and then he wrote this thing. He wrote that x to the n plus y to the n is equal to z to the n, and then said that for n bigger than 2, there's no integer solutions for x, y, z. And then that should be easy to prove. And then so he didn't prove it, and then he went on with his work. So it took people 2,000 years. Well, maybe not 2,000 years, 200 years. 200 years later, in 1988, somebody finally proved that this is true, and that was known as, you guys know what it was called? Called Fermat's last theorem. So, but this one isn't as hard as Fermat's last theorem. You can figure that out. All right. So it looks like we're starting to, feels like it. I mean, I'm comfortable with it. Are you guys starting to get comfortable with being able to do these problems? Oh, I lost the page. Oh, I hate it when that happens. So another interesting task is to, well, maybe we do some of these ones that are surfaces, multiple surfaces. Actually, before we do that, let's take a look at these problems over here. These are the interesting problems where you're given an integral, and then you're asked to switch the order of integration. And so for you to be able to do something like that, you need to redraw the whole thing so that you can get an idea of what you're looking at, because you know you can't just switch the limits of integration, because if you do that, then you'll have this one, the red one.
Yeah.
So, what? To switch the order of integration. Wow. It got worse right when I started. All right, so let's take a look at this one. And you know that you can't just, let me do something silly over here. You know that you can't just do that, right? Why not? What's wrong with this? What's wrong with this? Outer limits, outer integrals has to have constant limits, so you can't do this. You can't just blindly switch the limits of integration in the order of integration. So what you need to do is you need to actually take a look at those integrals, the limits for the integrals, and recreate your domain. So a good way, for me at least, the way I like to think about this is to try to look at the limits, write the limits like I do when I'm going from the drawing to the integral. Now you're going to go from the integral backwards, and I would still want to include the limits. So retranslating this, I have my y is my inner integral, and my x is my outer integral. And then my y goes from 0 to ln x, and my x goes from 1 to 2. And somehow I need to take a look at this and draw a picture out of this. Well, this is just y is equal to 0. Y is equal to 0. Y equals ln x. Now, if y equals ln x is too difficult to picture for you, well, that's not too hard. I was going to say, if it was too difficult, maybe you can solve for the other variable, but that just makes it kind of weird. It's x equals e to the y, which you'd have to draw with your head tilted. And you get your exponential function sideways. But this is the ln function drawn the right way. So this is the y functions. And then my x functions go from 0 or from 1 to 2. So I can see that my region is probably this thing over here. So now if I'm going to rewrite this in the reverse order, I knew that my graph had the y first and then the x. Now I want to redraw this where the x is first and then the y. I would set up my limits of integration. I would draw a line parallel to the x-axis. That's what I'm integrating with respect to first. And then I see when I'm going to enter my region and exit my region. I will enter my region when x is equal to e to the y. And I will exit my region when x is equal to 2. So those are my limits for x, the inner integral. And then y has to be constant, so my y value starts at 0 and it ends up here somewhere. So you need to find the intersection between the y equals ln x and the x is equal to 2. Well, I'll just put the 2 in for x, and you get ln of 2, which is a constant. It's a constant. I know there's an ln there, but if you have a number inside of the ln, it's a constant. It's 0.69 something. So my integral then would have the same integrand. The integrand isn't going to change, except my dx is going to be a dy instead, or my dy is going to be a dx instead. My x limits go from e to the y to 2, and then my y limits go from 0 to ln of 2. All right? Questions? All right, let's jump to one where they're describing a couple of surfaces. You want to find the volume between them. over some region, and see if we can visualize this in 3 dimensions also. So that would be 23 to 32 over here. Find the volume of a given solid. Should we do 25? So it's under the surface, x, y, z is equal to x, y, and above the triangle on the xy plane with vertices at 1, 1, 4, 1, and 1, 2. All right, well, before we get 3D on this stuff, let's just look at the region and see if we can find the functions associated with the region. So for that, I need to draw something in 2 dimensions, 1, 1, 4, 1, and 1, 2. So it's a nice right triangle. So really the only function I think I need to look for is that hypotenuse, because I know that this is one of the legs here is y is equal to 1, and here x is equal to 1. So we just need to find the equation of this thing. Well, what is it? Y equals mx plus b business. You have a couple of points to connect, or if you can find the y-intercept. Somebody tell me what it is.
Negative 1/3 slope.
3, maybe? No, 2 is over here. No. Oh. Come on. Seven thirds is the y-intercept? All right, I'm already doing it, so. 1 minus 2, 4 minus 1, negative 1/3. We got the slope right. So y minus, I'll pick this point, y minus 1 is equal to negative 1/3, x minus 4. So y is equal to negative 1/3 x plus 4/3 plus 4/3 and added 1 7/3. Yep. All right, so that's my function here. So since I have y solved for, I'm going to integrate with respect to y first. So if I integrate with respect to y first, I'm going to draw a line parallel to the y-axis, and I'll see when I'm going to enter and exit my region. So I enter my region here when y is equal to 1. That's this line right here. And I exit the region at this function minus 1/3 x plus 7/3. And then my x is going to go from 1 to 4. Okay. Let's integrate. My integrand is the function z, or f of x, y is equal to x times y. And I'm going to integrate with respect to y first from 1 to this function. And then I'll take my integral after I solve for that. Take the integral with respect to x, and my x limits go from 1 to 4. All right, let's do it. With respect to y, x is constant, so this will be x, y squared over 2 from 1 to this thing. see how this is going to go. These are y limits, by the way. I integrate with respect to y, and so x is the constant variable in there. So I have x over 2 times negative 1/3 x plus 7/3. That's the top limit minus x over 2 squared. And then you put 1 in for y. Oh boy. All right, I'm going to do some weird things to simplify my work a little bit. I'm going to take out a 1/3 squared in the denominator, so that's a 1/9, and multiply it by 2. So I have a 1 over 18 x, and then I have a negative x plus 7 squared. I really should be done with this by now, but I'm going to go through this. I could do it. 49 minus 14x plus x squared minus x over 2. And I get a 49 over 18x minus 14 over 18x squared plus 1 over 18x cubed minus x over 2. I can combine it, but I'm not going to. All right. So that's the inside integral. And we'll bring the outer integral down from 1 to 4 with respect to x. So these are just integrals, simpler integrals with respect to x. So the integral of the first one is x squared over 2. So I'll double the 18 down here. 36. So 49 over 36 x squared. Next one is x cubed over 3. I'll triple the 18. 36 plus 18, 54. The next one is x to the 4th over 4, 72. And then this is x squared, so x squared over 2 times 2 is 4. Right now my brain's I can't do this anymore. You can fill in the blank. I'm done. All right, is that good? Aside from this done stuff? Okay. So, yeah. Let's see if there's anything else interesting to do. Oh, how about 32? Like, the one we were just doing? It's a good question. Yeah, so the x and the y look like they're going to behave the same way when you integrate it the first time. And this, yeah, like AJ was saying, this is still going to be a line of some sort. So if you solve for x here, you're still going to kind of get the same situation. All right, I don't know if I want to do 32. 31? All right, well, let's take both of them and we'll decide.
I think we want 32 then.
Look how hard 31 looks. All right, which one are we going to do?
32.
32. All right, fine. So, okay, bounded by two cylinders, they have the same radius. So, let's pretend it's 1. No, let's keep it at that. So, I don't know if you guys could picture this, but let's see. So this is 3-dimensional, and what we want to do is we want to break this down so we're seeing what's flat on a 2-dimensional plane so we can establish some sort of domain. We have x squared plus y squared is equal to r squared as this first cylinder going along the z-axis. And then here we have y squared and z squared, so probably going along the x-axis, a cylinder that's going to be intersecting like that. And you may have seen something like this in your Calc 2 where you're trying to find volumes of things, but this is going to be a lot easier. Doesn't look like it right now, but hopefully it'll be easier. It'll probably be just as hard. Okay. So what we want to do is we want to take a look at this. Let's say we want to integrate this as a function of z is equal to f of x, y. Over some domain D on the xy plane. So what we want to do is, if I can twist this over and take a look at it. Yeah, so you want your point of view looking down, and all you're really seeing is your domain is that circle, a radius r. That's what you're seeing on the xy plane. Okay? Now, if that's what you're seeing on the xy plane, you have to establish what your surface function is going to look like. And what is your surface function going to look like? Well, your surface function looks like it's, if you imagine this, it's going to be this cylinder, just the top part of the cylinder would be the function on top, and then you could look at the bottom part of the cylinder, it would be the function in the bottom. Okay, so our two surfaces, it looks like we have a volume that's bounded by two surfaces. One would be the top part of that cylinder, the other one would be the bottom part of the cylinder. You with me so far? You sure? No. What? Why, you don't like my picture? Can you graph that? Come on. So, x squared plus y squared equals, let's let r equal to 1. And then we'll take a look at y squared plus z squared equals to 1. So this is the initial graph that we were looking at, right? This is how it looks like. And I would be interested, so are we agreed that this is our domain, that our domain is just a circle if you look at it straight down, and that's all we're seeing, right? Okay. I only had like a quarter of the class nod and say yes. Are we agreed that that's your domain?
Yes.
Okay, good. So now I need to convince you that your functions are the top half and the bottom half of the cylinders, because you're looking at that space in between. So what we need to do is that function, or it's not really a function right now because it's a relation, that relation that we have between y and z is what we're going to want to try to exploit. And what we want to do is we want our z to be the function of x and y. So if we take this and solve for z, z is going to equal to r squared minus y squared with a square root. Am I missing something?
The plus or minus determines the circle.
Plus or minus determines yeah, she said. So if we take our function, or our graph, oops, and instead, this is going to look a little funny because of the way the graphing calculator renders the surfaces. If we say z is equal to the square root of r squared minus y squared. Technically, it should go all the way down, but there's some issues with the rendering where it doesn't make it go all the way down. But this is your, let me change this into a brighter color. I don't know if that helps. But this is the top part of that surface that we're talking about. And again, if we're only restricting this to the circle, that's what we're seeing, the top part of the circle, or the cylinder. And then right now, we're not seeing the bottom, but we'll incorporate the bottom part of the cylinder by just throwing a negative. So if we take the same function, and put a negative in front of that with a different color, then we see the bottom part of the circle, or bottom part of the cylinder. That's going to be the space in between those two things. Okay? Is that okay now? Does that make a little bit more sense than before? So it looks like we will have two functions. The top function is z is equal to r squared minus y squared. The bottom function is negative z is equal to negative square root of r squared minus y squared. And then if you're going to subtract them, you're essentially doubling this. It's the same thing as if you just went from 0 to the top and then you doubled it. So this is going to be the function in your integrand that goes inside of your integral. So now you can take it a step further. We still haven't negotiated the domain D, but at least now we know what's going to go inside of the integrand. Okay? All right, so that's the first step. Next step is now we're looking at this integrand. So we need to do that finding limits business again. So at this point, you can decide whether to integrate with respect to x first or y first, and at this point, it doesn't really matter. We could probably use some symmetry to simplify our work a little bit. But let's make it really hard for ourselves and see how this is going to work. So pick a variable we want to integrate with respect to. Let's integrate with respect to y first. We will draw a line parallel to the y-axis and notice where we're going to enter the region and where we're going to exit the region. So if we take our equation and solve for y, we'll see those limits pop out, right? So it looks like I'm going to enter my region when y is equal to the square root of r squared minus x squared. We'll call that negative because it's below. And then we will exit the region y is equal to positive square root of r squared minus x squared. Okay? Those are my limits for y. Negative square root of r squared minus x squared, positive square root of r squared minus x squared. Limits for x? Constants going from negative r to r. So now that we have that, we can rewrite our integral. We got a 2 sitting out there. We have in the integrand r squared minus y squared, and we decided we're going to integrate with respect to y first. dy, y goes from a negative square root of r squared minus x squared to a positive square root of r squared minus x squared. And then our x is going to be from negative r to r. Okay. So this isn't impossible to do. You can certainly figure this out by hand. Might do a little trig substitution or some other substitution to begin this integral. Might be beneficial to integrate with respect to x first, because I'm looking at this with respect to y, and then trig substitution is the only thing that comes to mind here. So if I integrate with respect to x, the integrand didn't have any x's, so that might be beneficial if you do it that way, if you were doing it by hand. Because if you integrate with respect to x, this is constant, then you'll have an x, and then you'll just put in the limits, and maybe it'll be easy. I don't know. Yeah, it'll be easier. Okay. Say again? It would be the same. They would look just as difficult here. Yeah. Yeah. Should we set it up? Got me thinking about it now. Is it really going to be easier? Let's see.
You're going to have y's and your limits and x's and
The integrand is not going to change.
Yeah, but the limits, after you take the first way, you're going to end up with the square root of stuff.
Right.
Yeah. And then you have to take the integral anyway, and then put in limits.
Yeah, but then, why? Okay. Let me convince you that it actually is easier. So I'm going to integrate with respect to x first. And my x is just like this y is equal to, except x is equal to the square root of r squared minus y squared with a negative, and r squared minus y squared with a positive. And then y goes from negative r to r. So my integral would look like the same integrand, r squared minus y squared, except now I'm going to integrate with respect to x first, where my x limits are negative square root of r squared minus y squared, positive square root of r squared minus y squared. So what I was trying to say here in terms of the actual integrating work is that when I integrate this with respect to x, there's no x's in there, so everything's a constant. So it'll just be x times this. And then I put in my limits for x, which is negative square root of r squared minus y squared, positive square root of r squared minus y squared. So if you put that in for x, yeah, the square roots are going to cancel. So x, this is your x. This is already here. So the square roots would go away. Minus, and then I have a negative for x, which is just going to double this whole situation. So this will just be 2 times r squared minus y squared without the square root now. So now this is where it becomes easier. And then you put that in for your integrand. So your integral, back to your integral minus r to r of now, your integrand now becomes 2 r squared minus y squared dy, and you take the 2 out, and then that's just an easy integral. So it did turn out to be easier if we integrated with respect to x first. Let's do it by hand.
So when we were making the integral, why did we choose one function?
Because that's what it has to be. That is the top surface minus the bottom surface scenario. So if you're trying to find the space between two surfaces, it has to be the top minus the bottom. So whatever the top surface was and the bottom surface, somehow you need to convince yourself that the top surface is this sideways cylinder, but only the top part of that sideways cylinder. And the bottom surface is the bottom part of that sideways cylinder. No, not for this case. Okay? Why can't what? I suppose you can, and then you're integrating instead of dy dx, you're going to be integrating dy dz. But it's going to be the same amount of work. Okay. So integrating over a circle like this kind of is a good lead into our next topic. So instead of integrating over a circle where we have to find all these square root business things, we might see if we can approach this a slightly different way where the integrand might look a little nicer. I don't know if this is the best place to start, but let's give it a shot. Let's take the same problem and let's see if we can find new tools to solve for this problem. So the big issue, I don't know, the big issue probably is to figure out your integrand, right? But the other big issue is that this is your domain. And so what we want to do is, instead of saying, okay, find limits for x and y, instead of trying to find limits for x and y, we have a relationship with x and y and the polar coordinates r and theta. And so what we might be interested in doing instead is that use the idea of r and theta to describe this region. So this r isn't good here. It's not the same r. R and theta in polar coordinates. And so what we want to do is let's see if we can describe this region using r and theta. And I'm gonna change this into a capital R, just so it's not that little r. Yeah.
So the r and polar coordinates is talking about the radius of that circle, but the radius of that circle is the radius of the cylinder.
Yeah, that's not that important. All right, so keep your eye on the little r and big R right now, okay? So let's see how we're going to move here. And I don't know if we're going to get to your question today, but we'll see. If I wanted to describe this whole circle, a radius capital R, what I could do is I can describe my R as some radial distance from the origin. So imagine your R going from the origin outward, and how far would you go? So if you go from 0 to big R, you would imagine taking this and making a line segment from 0 to this r. Okay? Now, that's not a circle, and it won't be a circle until we do something with theta, and theta, you know, can go around. So if I swing this line segment all the way around and let my theta go from, say, 0 to 2 pi, then I will have my whole circle completed. Essentially, you can think about that. You're making rings, depending on what your theta is. So my theta going from 0 to 2 pi, you're making rings. So this then would describe a circle, a radius capital R. Okay? So to get a better feel for this, let's change some things with these limits. So let's say I let my R go from 0 to 1, and I let my theta go from 0 to pi over 2. What am I drawing here? Semicircle? Quarter circle? Radius? So I go from 0 to 1 with my R, and I take that and I spin that until I get to 2 pi, and then I'm going to get that piece of the circle. All right, let's change it up now. What if I let my R go from 1 to 2, and I let my theta go from 0 to pi? What is this going to look like? So my radius goes from 1 to 2. So I only have this piece that I'm going to spin around from 0 to pi. So this goes from 0 to pi, this goes from 0 to pi, and so all this stuff in here and not this stuff. So that would be the region I would be describing. Okay? So if I let my R go from 0 to 1 and my theta go from negative pi over 2 to pi over 2, what do I have? Right side or left side? Right side. You start with negative pi over 2. You go from 0 to 1, and then you swing that all the way around to positive pi over 2. So it's all these. So it's just going to be the right side of the circle. Okay? So that's how you would describe your polar coordinate stuff. And then don't forget that your polar coordinate relationship between the Cartesian is r is equal to x squared, or r squared is equal to x squared plus y squared, and theta is equal to arctan or something. And then x is equal to r cosine theta, y is equal to r sine theta. Okay? So we're going to dive into this in a lot more detail tomorrow, and we're going to switch variables when we're integrating from x, y to r theta. Now, when have we switched variables before in when we're integrating? We've switched variables when we're integrating a couple times back in Calc 2.
For a nicer exchange and nicer interval. Oh, and also DS and stuff.
No.
No?
Last U substitution. When we did a U substitution, we switched. When else did we switch integrals? or variables? Trig substitution. When we did u sub or trig sub, we switched, right? We switched from x to u, or we switched from x to theta. What did we have to do when we switched from x to u, or when we switched from x to theta? Change limits. What else?
You have to like move all the junk to the other side.
Your dx. We had a differential dx, and so we need to change that. So all those things apply here. We're doing a u substitution or a trig substitution, but in two variables. So we're going to need to switch things around. We're going to need to change the limits, and we're going to need to change our dx, dy, our dA. That needs to change into something with a dr, d theta. Okay? So we'll figure that out tomorrow.